Capacity planning is an ongoing cyclical process. There are various common measures such as VM instance capacity, disk performance, network throughput, and workload estimations. Ultimately, you need to be able to answer the question, is there sufficient resource with reasonable certainty? One of the key design principles in this course is to allow other factors to influence your design first and then come back and dimension the design later. You might have to change some of the design for capacity or for better pricing, but at least you'll make these adjustments knowing what benefits you're trading for reduced cost or better capacity management.
So let's start with capacity planning. It's really a large cycle. First, you forecast. If you don't have any previous data, you honestly just pull something out of the air. Then you decide what is it you're going to allocate, what resources are going to be necessary, and then try to go and get approval for that. If you get the approval, you get the funding, or the approval for funding, since cloud is pretty much an OpEx versus CapEx, then you go ahead and deploy. Once you monitor and use the indicators on production, you can probably utilize this to better forecast. How far were you off on your predictions, and then what learnings can you take, and simply repeat that process. So when it comes to forecasts, we want to monitor growth, we want to try to predict future demand, and plan for future launches. So as we start to make changes, feature enhancements, etc. And remember, forecasting is going to be iterative. So what was the prediction last time? Compare it with the actuals, whether we're high or low. Give some kind of error budget. Pretty much in any consulting model, you always say, well, the job will take 10 hours, but we're going to add 2 or 3 for what ifs, because nothing ever goes exactly the way we predict. And so then try to make a more accurate prediction next time. So this way, forecasting converges on a practical value by learning from previous errors. So something to keep in mind is, or ask yourself, what other values should you potentially include in your forecasting estimate? So in forecasting estimation, testing simply beats tradition. So don't mistake launch demand for something stable, or you might actually over-provision. A great example of this is when companies release a new game. All the news and the hype is out there, then they get a huge influx of new users, and they have to design a 10x architecture to support this. But as the game starts to stabilize and the popularity waxes and wanes, or if it's competing with another one, you'll start to see just kind of shaking out of all the steady users, and that's pretty much what you have to work with. So don't get all excited about that launch demand. Wait for stabilization to occur. But always remember to include the M+2 servers, or else you're going to potentially risk an overload situation that we've covered earlier. Always add headroom to deal with nonlinearity of demand. So this way, if you start to experience individual spikes, etc., and add overhead to instance estimates. So if you always measured, say, 10,000 QPS for performance, understand if that's going to change in the future. Perhaps the way the network is designed, the software, etc., you may not get that linear type of growth projection. So instance overhead estimation. How do you kind of overestimate without overly estimating? Well, if you take a look at 100% of the capacity of a VM, some of it is going to be consumed by overhead right out of the box. So if you can't test, just say 30%. You're only going to get 30%, especially because you don't want to run things at 100% due to potential cascading failures. Now, we do recommend that load testing be done, especially if you're comparing it to on-premise to the cloud. One thing to also to keep in mind, if you're moving from an on-premise VM with, say, 8 cores, that actually represents 16 virtual cores inside of the Google Cloud Platform, because every vCPU is a hyper-thread, so that one there can easily be identified. Second, what about the operating system image? Just the fact that you're running an OS takes up capacity, and so test different types of images. In fact, our performance team has identified that Ubuntu performs the best in pretty much all platform benchmarks when it comes to Google Cloud Platform. Understanding hardware architecture. Remember, different zones have different hardware components. In fact, now when it comes to Compute Engine, you can actually go in here when you're creating a compute instance, and before you'd have to look up the different zones and instances to try to get a guesstimate of what you might get. But notice here, when you create an instance, let's go ahead and re-authenticate here. Okay, so when you're creating the custom instance, notice here there is no selection on what hardware type you're going to get, because our data center is actually kind of peppered with many different technologies. So we've got Skylake, which just came out. We have Haswell processors, Sandy Bridge, Ivy Bridge, etc. If you click on Customize, notice here then you can actually choose and prefer a CPU platform. And your application may actually benefit from the new instruction set available in the CPU processor type. So that also is something to take into consideration, and which is why you should benchmark each one of these different processor types to determine which may or may not benefit. you're going to pay the same price for each one. So it really doesn't matter. It doesn't matter which one you get because you're going to pay the same one, but you certainly could see a difference in your performance benchmarking. Now, turn off the OS firewall. We already have that covered for you. Our firewalls are already in place, and that's going to be a pretty considerable difference. Also, if you're running something like Windows, which is very known for swapping data to a page file, try looking at local SSD if you can afford it, because local SSD is in 375 gig increments, and that way you can do persistent disk if you have large persistent disk. Standard HD, I should say, for that. So there are a number of different ways to try to eliminate that. And plus, what you'll notice is when we create virtual machines, we also tell you it's not 4 gigs of memory, it's 3.75 or some decrement. Because you remember Apple on that lawsuit about iPods not really being 16 gigs, it's because they did not really kind of disclose all of these overhead estimations. Passed it on to the consumer. It doesn't work out well. Anyway, if we take a look here, let's take a look at persistent disk. So one thing is that IOPS are constrained by potential CPU. So even though you can scale storage, and I'll show you an example here. So if you're in Compute Engine and you want to know that you can scale storage and get disk IOPS, so if you go under disks, click on Add Item here. So we're going to add a new disk, and what you'll notice here is if I choose standard persistent disk, I can choose 10 gigs and I get a fixed performance. But if I increase it to 100 gigs, you'll notice that my performance will continue to increase. This is fantastic. But what it is we're simply enabling our software-defined quotas, and we are enabling that disk to perform to that level. But if you don't have enough CPU to drive the disk I/O, well, then that could potentially be a bottleneck. So keep that in mind, that oftentimes a higher amount of CPU is necessary. In fact, if you want to max out a standard SSD, you need at least 4 CPUs most likely to drive that. So also consider I/O burst, because our network is very, very consistent, but you could have big spikes, especially if you're flushing data to disk for a database, etc. Keep that in mind. And then, of course, if you're trading up for performance over capacity, you need to determine whether you're going to choose SSD or standard HDs. Now, there are some open source disk measurement tools which you can use to try to create those benchmarks, but we're going to get into kind of one universal one here in just a bit. And then, of course, network capacity. If you remember that network capacity, especially for VMs, is limited by the number of CPU cores. So you get 2 gigs of throughput for every CPU core. We allow up to 16 gigs maximum. So what that means is if you want to max out the potential of a virtual machine's network, 8 cores will get you to that limit of 16. Now, you still may not have enough CPU to drive that much, depending on your workload, but at least we will open up the quotas for you. Secondarily, all VMs come with both internal and external IPs. Internal IPs are on a much faster network because they don't have a lot of the external overhead and inspection that's necessary. So if you benchmark the two, you will see definitely a large discrepancy in latency between the two. Internal networks are always faster. Then workload estimation. So understanding what the throughput could potentially be. Well, that can vary quite dramatically. What kind of request do we have? What is the size of the payload? Remember in the photo application, we were talking about the attributes. Some of them would be high throughput, high disk I/O, etc. So understanding your business logic and what effect that they might have. There's a number of open source tools to kind of help you in benchmarking that. But what we recommend is the PerfKit benchmarker. So this is an open source project on GitHub that Google has created. It originated here. It actually includes 28 open performance benchmarking tools. And what we're trying to do is make it kind of the standard for all benchmarking. So this way you can apply it to all cloud providers and understand, who has a better this versus that. And in this case, you'll see a lot of public information on utilizing PerfKit benchmarker, and it pretty much can test almost anything that you need. And we've actually designed everything around PerfKit. So in our performance updates, we will actually try to benchmark it against PerfKit results to ensure that we have improved our overall performance. So, and this is also something that where GCP services, we actually design these to achieve efficiency at scale. So some people will test a single server and say, oh, well, some other cloud provider is faster. Well, we didn't design it for that. We're really designing to get to the bleeding edge. When you're getting in hundreds of VMs, thousands of drives, etc., you're not going to hit that overhead. Because, again, when we talked about distributed state and all the other distributed natures, you may exchange latency, especially early on in the design. But as you start to scale, we will be able to maintain that low level of latency where it wouldn't be possible in some other solutions. So in this case, now we're going to move on to the next step, and that's allocate. So forecasting is going to tell us basically how much capacity, how much we're going to potentially allocate. So allocation is going to tell us how much resource is going to be necessary to provide that capacity. So think of it this way. It's a ratio of resource to capacity. Maybe I need 2 terabytes of physical PD to give me 1.5 terabytes usable, just as a simplistic measure. So doing this, you have to kind of ask your questions, estimate what capacity is required based on our forecast. How do we validate those estimates? We're going to do so with load testing, and then calculate the resources required based on that particular ratio. So another example here is our forecasting. So our service is growing. We expect the demand for storage throughput is going to increase by, say, 30%. So we've already measured our QPS, and we're going to add 30% to that. So we now have a new number. And so we understand that our new throughput capacity is 327,600 QPS. Well, let's just say we're applying this to Bigtable. Well, in this case, our documentation on Bigtable and benchmarking does show you get about 10,000 QPS per Bigtable node. And so that means we have a 10,000 to 1 ratio. So for every Bigtable node, we can do 10,000 QPS. So in our case, we just simply divide the number of nodes our QPS by 10,000 to come up with about 33 Bigtable nodes. And we can benchmark that and kind of test it out, but it's a good rough estimate if we're starting from nothing. I would imagine we're increasing, so we would start with something. So other things, before you just simply add more hardware to the component, always try to see if there's opportunities to improve. Could you start enabling caching? Could you cache data in Memcache or local SSD or something else that might be as beneficial? Any tuning, right? Sometimes we just get a little lazy and we say our applications are super efficient, but sometimes this can be really fun to see if adjusting code so it doesn't use as much disk I/O, allocates memory more often. Maybe that can really help. Better algorithms, or even alternative services. So when we talked about our photo application and we're running this homegrown ETL processing script that we made, maybe data flow is going to be a better service. It's a fully managed service. Maybe it scales better. The algorithms are tuned. Perhaps that might be a consideration. Finally, with all of this, if you've been using your service level objectives and indicators, you now have data-driven support to drive these numbers for recommendations. So it should be a lot easier to get approval. You have the data, you have forecasting, you can calculate what the pre-approved costs are versus just randomly getting a quote from a vendor, right? That's typically what most people do. So now we're going to go to the deploy phase. First, test. Always work through the issues before serving it to your users. Because remember, we're trying to maintain the integrity of our users. So we want to identify any bottlenecks and then make this as painless as possible. If we can do dark launches, so this way we're doing testing in an isolated launch, and then of course doing a slow stage and iterative process. Canary deployments, slowly rolling out, so this way we do, if we do affect our customer base, it's a very small percentage. So in this case, we always want to consider that balanced approach to the launch process. We want to make it easy to use, but it should also be customizable. We want to be able to catch obvious errors and handle simple use cases, but we understand that there are some of those more difficult, hard to find. So we want to try to build in some kind of unit testing for reproducible or hard issues. So on and so forth. So you can kind of get an idea here of bouncing back and forth, trying to find that kind of happy medium when it comes to your launch process.